All right. Now we're going to talk about enthalpy related to enthalpy actually measured in a reaction, and this will eventually lead us to calorimetry. So when enthalpy, which is delta H, changes, it tells us the enthalpy of the products minus the enthalpy of the reactants. So it's kind of the difference of the two, and depending on if more energy is given off by the reaction than is taken in, then the enthalpy is negative, and so the products technically have lower enthalpy than the reactants because the change in that is related to that. So this idea of delta H is equal to the H of the products minus the H of the reactants. So when we measure the delta H of a reaction, we can actually learn a little bit about um, the enthalpies of the reactants and the products. So delta H is called the enthalpy of reaction or the heat of reaction. It's what we measure. So you've got this example of a hydrogen balloon exploding here. Um, yeah. Okay, so what are the things that we need to note about enthalpy? So one, enthalpy is an extensive property. What does extensive mean? Well, it means that, pause it for a sec. All right, sorry about that pause there. Okay, so enthalpy is an extensive property, and basically what that means is that the more reactants that you have reacting together, the greater the enthalpy is going to be. So 1 mole versus 2 mole, you're going to increase the enthalpy according to how many moles are reacting together. So it's dependent on quantity, on an amount. Second part, the enthalpy or the change in enthalpy is equal for a reaction in the forward direction is equal in size but opposite in sign to the delta H for the reverse reaction. So we're probably haven't spent really much of any time in first year chemistry talking about reactions that can go in both directions. That's something that we'll get to in this course. And so if you have a reaction, so in the case of the production of water, so when you have hydrogen combining with hydrogen gas combining with oxygen gas to produce water, you have a certain enthalpy value, and that's going to be negative because it's very violent. Well, the opposite, so let's say we wanted to take water and split it into hydrogen gas and oxygen gas, which is called electrolysis. Well, that would require the same enthalpy, but in the opposite sign. So you would have to add that much energy to the hydrogen or to the water to split it into its separate components. And um, also, one thing about enthalpy is that the reaction is dependent on the states that the products are in, and also the states of the reactant. So the enthalpy value is going to be different if it was hydrogen gas and uh, oxygen gas versus liquid hydrogen and liquid oxygen. So different values depending on the states that are present at that point. All right, so we're going to go right into calorimetry. And calorimetry is utilized to actually measure the enthalpy. And this is basically related to the fact that we can't know the exact enthalpies of the reactants and products, but we can measure the change in enthalpy. And we do that using calorimetry. Now, we measure calorimetry. You did it with the two styrofoam cups. You measured some temperature changes there, and that's related to that. When we did the bleach and the, I forget, oh, the unknown. So we've got, but they're always open, right? They're open to the atmospheric pressure, so therefore, for the most part, the pressure is held constant. Now, certain substances have certain what are called specific heat, or they have a specific heat capacity, the ability to absorb a certain amount of heat before it changes the substance's temperature. Okay, so the amount of heat energy required to raise the temperature of a substance by 1 Kelvin or 1 degree Celsius is its heat capacity. And you notice in this table that certain things have higher or lower heat capacity, meaning they can absorb more heat before the temperature actually changes. So water in this table has the highest heat capacity, meaning it takes a lot more energy in the form of joules to change water from 1 degree Celsius to 2 degrees Celsius. If you have, and that's per gram. So 1 gram of water requires 4.18 joules of energy to increase the temperature by 1 degree Celsius. And we define specific heat capacity, or simply specific heat, as the amount of energy required to raise the temperature of 1 gram of a substance by 1 Kelvin. So that's our specific heat table there. So how might we apply it? So specific heat is equal to the heat transferred divided by the mass of a substance times the temperature change. So you have C with the subscript S is specific heat, Q is the heat transferred in the reaction, mass of like a substance that you're using, and also the temperature change. So when we carry this out under constant pressure, we've got kind of like a cap, thermometer in there. May or may not use a cap. We don't usually use them in chemistry, in AP Chem, but some fancier ones, they utilize that. Let's see, by carrying out, so we can measure the specific heat change, and we can use the knowledge of like this. So we typically do it in a container with water, and water is basically our substance that we're measuring the temperature change in. So therefore the specific heat of water, which we saw on the table, we can then use the equation to work to figuring out what Q is for a specific reaction. So we kind of rework the equation in such a way so that Q is equal to the mass, and the mass can be related to the volume by using density. So we can figure out, okay, what mass of this substance do I have of water, and then I use the specific heat of water, and then I use what the change in temperature. So I take my starting temperature, my ending temperature, now I've got a value. Now I can calculate Q and actually figure out what the heat of the reaction, which in a constant pressure environment, Q is equal to delta H. So therefore, we can solve for enthalpy. Okay, now that's true for a system like that, but let's say we want to measure the combustion of something that is very explosive, so it's very difficult to actually keep the heat within the container. A lot is kind of given off to the surroundings. Well, in that case, we use what is called a bomb calorimeter, and that is where we have a container kind of trapped or surrounded by water in such a way so that all of the heat given off in the reaction is absorbed by the surrounding water, and then gives us a pretty close approximation to the enthalpy change of the whole reaction. Then you kind of calculate it out to figure out how it changes. And you can kind of look at that model a little bit more. Okay, so because the volume in the bomb calorimeter is constant, what is measured is really the change in internal energy. And this is what we kind of derived in class today, where we saw that, so when the volume is held constant, we're actually not solving for delta H, we're solving for delta E in the process. So slightly different than delta H. But for most reactions, the difference is really small, and so we can call them equal. Now, we don't have a bomb calorimeter in the lab, so we won't be able to do those type of experiments. And that's it for today.